Good day everyone, we are the Group 2, which is Group Catalysis. And our report for today is entitled Monolithic Catalysis in Automotive Exhaust Systems. I am Zahir Ibeik and I am going to start with an overview of our report. First, we have our introduction, our theoretical framework, our related reviewed literature, and our simulation design. The next is our data presentation and analysis. And next is our challenges, scale up, optimization, and conclusion.
The following presentation on monolithic catalysts in automotive exhaust systems was developed with the assistance of generative AI. Large language models were used to structure the reporting script for clarity, generate an outline for cohesive discussion, and cite the references used. All AI-generated content was reviewed, verified against the primary source material, and refined for technical accuracy and academic integrity.
First, let's start on catalysis. What is catalysis? Catalysis is the process of increasing the rate of chemical reaction by adding a catalyst. While a catalyst helps speeds up the reaction without being consumed in the process, and it works by providing an alternative reaction pathway with a lower activation energy. To sum it up, the catalyst is the process of increasing rate, while the catalyst is the one that speeds up the reaction. The role of the catalysis. Catalysis plays a vital role in both biological and industrial processes. In living organisms, catalysis such as enzymes allows essential reactions to occur fast enough to sustain life. And in industry, catalysts are used to manufacture chemicals more efficiently by increasing reaction rates and improving the product yield. And catalysis is also involved in the production of more than 85% of the chemical products that we use today are available in our daily life. It contributes significantly to industrial and economic activity, accounting for a large portion of processes in developed countries, and this highlights its importance in modern chemical engineering. Types of catalysis. Catalysis can generally be classified into two main types, which is the homogeneous and heterogeneous catalysis. The main differences between these two is the physical phase of the catalyst relative to the reactants. And understanding this distinction is important because it affects how the reaction occurs, how the catalysts are covered, and how they are applied in the industry. Now let's see some of their differences listed. In the homogeneous catalysis and reactants are in the same phase, which is usually a liquid phase. And they are also in a solution-based reaction, and the example of this is that they are acid-base reactions, oxo process. Well, in homogeneous, they are also difficult to separate the catalysis from the products, and they are also often high selective, and that recycling this catalysis is quite challenging. Well, on the other part, which is the heterogeneous catalysis, the catalysis and reactants are in different phases, usually in a solid catalysis plus the gas reactants. Well, also the reaction occurs on the catalyst surface. And in the heterogeneous part, it's also easy to separate and reuse the catalysis. But it's also more suitable in the industrial processes, and they are more stable under harsh conditions. Well, since our topic focuses on the automotive exhaust systems, which involve the gas-phase pollutants reacting on the solid catalysis surface, we will focus more on the heterogeneous catalysis in the succeeding sections. Monolithic catalysis. It uses a structured catalysis, typically in a honeycomb shape, which you can see in the picture above, with many parallel channels, and these catalyses provide a large surface area for reactions while allowing gases to flow efficiently, resulting in a low pressure drop and a high mass transfer. While monoliths are widely used in automotive exhaust systems to convert the harmful gases like CO and NOx and hydrocarbons into less harmful products, the regular structure also makes them more predictable and efficient compared to traditional fixed bed or slurry reactors. In the review and related literature part. So in the first study, it is shown that the structured reactors, and especially monoliths, offer the precise control over catalytic processes that traditional reactors cannot achieve. While the regular channel design improves the flow distribution and diffusion, it also reduces the pressure drop and ensures more predictable reaction behavior. So this makes monolithic reactors the preferred choice for the automotive, exhaust, and environmental application. They are also adaptable for small-scale laboratory or pilot operations and highlighting the versatility in both research and industrial settings. For the second study, it discusses the general use of the monolith reactors in exhaust gas cleaning. It explains that these reactors are widely applied in automotive systems and industrial processes due to their high efficiency. One key finding is that monolith reactors provide a large catalytic surface area while maintaining a low pressure drop. All this allows the gases to flow smoothly while still undergoing the effective chemical reactions. However, the study assumes that the steady flow conditions and uniform distribution of reactants, which may not always occur in the real systems. It also highlights that performance can be limited by mass transfer resistance, meaning that the proper reactor's design is essential for optimal efficiency.
Simulation design specifically for the monolith reactors for emission control. Modeling strategy. Monolith reactors are widely used in catalytic converters to reduce pollutants such as CO, NOx, and hydrocarbons. In simulation studies, the reactor is typically modeled using computational fluid dynamics, which solves the conservation equation for momentum, energy, and species transport. Because the monolith consists of thousands of small channels, models usually represent a single representative channel. Gas flows through this channel while catalytic reactions occur on the coated walls. The model integrates fluid flow, mass transfer, heat transfer, and catalytic reaction kinetics, allowing researchers to predict pollutant conversion, efficiency, and optimize catalyst geometry. Reaction kinetics. The most important part of the model is the catalytic reaction kinetics. In emission control systems, pollutants are converted through heterogeneous catalysis, occurring on the catalyst coating inside the monolith channels. Typical reactions include oxidation of carbon monoxide and hydrocarbons as well as the reduction of nitrogen oxides. The reaction rates are usually expressed using Arrhenius type equation, which relates the reaction rate to temperature and reactant concentration. The simulation must also account for the adsorption and desorption on catalyst surfaces and diffusion from the gas phase to the catalytic wall, which strongly influence overall conversion. Boundary conditions. To accurately simulate reactor performance, appropriate boundary conditions are defined. At the inlet, the model specifies the gas velocity, temperature, and composition of exhaust gases, such as carbon monoxide, hydrocarbons, and nitrogen oxides. At the outlet, the pressure is usually fixed near atmospheric conditions. The channel walls represent the catalytic surface where reaction occurs. A no-slip condition is applied for velocity, and the heat transfer between gas and solid catalyst is included. These boundary conditions ensure that simulation represent realistic operating conditions of catalytic converters. Computational details. The computational model solves the governing transport equation for fluid flow, energy, and chemical species. These equations are typically solved using the finite volume method in CFD software, such as the ANS, YS, Fluent, or COMSOL. A structured mesh is created inside the monolith channels to capture concentration and temperature gradients. The simulation output includes pollutant conversion, temperature profiles, and species concentration distributions, which helps engineer optimize catalyst designs and improve emission reduction performances.
In automotive engineering, we face a constant battle. How do you clean the air without choking the engine? If we use a thick solid filter, the back pressure would kill your performance. The solution is the parallel channel monolith. This design is the ultimate back pressure balance. It provides a massive surface area for chemical reactions while allowing the engine to breathe with almost zero resistance. It's a perfect compromise between raw power and environmental protection. Here's the clever part. Size matters. Because these channels have such a tiny hydraulic diameter, The exhaust gas doesn't swirl around in a chaotic mess. Instead, we keep the Reynolds number low, forcing the flow to become laminar. This isn't just for show, it's functional. In a stable laminar flow, the gas moves in predictable layers. This allows pollutant molecules like CO, HC, and NaOX to migrate efficiently from the center of the gas streams to the walls, where the catalyst is waiting for them. However, physics can only take us so far. We need the chemistry to wake up. During a cold start, the system is kinetically limited, following the Arrhenius equation. The reaction rate K stays low until the engine hits the light of temperature. But once the thermal threshold is crossed, the activity surges. At this point, this chemistry is so fast that the only bottleneck left is physics. The system becomes mass transfer limited, meaning its success depends entirely on how quickly those gases can physically reach the active sites on the channel walls. From a cold ignition to high-speed cruising, the monolith is a masterclass in the interplay between transport and transformation. Now, we're going to talk about the fluid dynamics behind it. As you can see on the slide, equation 1 and in equation 2 is the Navier-Stokes equation, and equation 3 is the species transport equation. So we use the Navier-Stokes equation to map out gas velocity and pressure, but we also need to track the pollutant themselves using the species transport equation. We're looking at how molecules like CO and NaOX are pushed along by the flow and how they diffuse toward the wash code. To keep the math elegant, we use a Lewis number of unity, where heat and mass diffuse at the same rate. This makes our transport constant, the Sherwood and Nusselt numbers, numerically identical, greatly simplifying our thermal and mass analysis. Now for the clever part, the instant reaction rule. In our models, we assume a constant wall concentration of 0. This represents the mass transfer limited regime, where the catalyst is so efficient that the moment a molecule touches the wall, it's instantly converted. By modeling these channels as perfect squares, we can accurately simulate this limiting case. It proves that the only bottleneck for a total purification isn't the chemistry. It's simply how fast we can physically get the gas to touch the catalyst. It's a perfect balance of hydrodynamics and high-speed chemistry, all working together to keep the air clean. Moving on, first let's talk temperature. Heat is the fuel for the reaction itself. By increasing the temperature, we give molecules the kinetic energy they need for faster, more frequent collisions. Then, there's pressure. When we increase the pressure, we are essentially forcing gas particles closer together. This increases both their concentration and their residence time inside the reactor, which means higher pressure means more frequent collision within the catalytic walls. Ultimately, higher temperatures and pressure create the perfect storm for optimization, ensuring that every molecule has the best possible chance of being neutralized before it hits the tailpipe.
Good day. For the data presentation, we are investigating monolithic catalysts in automotive exhaust systems based on the comprehensive research by Gaspar, Fornaciero, and Hickey. The core of a modern converter is a honeycomb-shaped ceramic or metallic monolith substrate coated with a porous aluminum wash coat, which supports active noble metals such as platinum, palladium, and rhodium, alongside series zirconia oxygen storage promoters and barium or lantana oxide stabilizers. As shown in Table 1, different engines present unique chemical challenges. While standard 4-stroke engines are balanced, diesel and lean burn engines operate with a massive excess of oxygen. Our performance data in Figure 2 highlights the stoichiometric window. When the air-to-fuel ratio is precisely balanced at a value of 1, pollutant conversion jumps to peak levels exceeding 95%. However, high concentrations of hydrocarbons can actually inhibit nitrogen oxide reduction, essentially crowding the catalyst surface and slowing the cleaning process. We also investigated how fuel type and catalyst loading dictate selectivity, ensuring we produce harmless nitrogen gas rather than greenhouse gases like nitrous oxide. In Figure 13, we see that performance is highly sensitive to the fuel type. An alkene, like propene, allows the catalyst to reach high efficiency very early, whereas an alkane, like propane, fails to exceed even 10%. Furthermore, Figure 15 shows that while 10% silver loading results in poor selectivity, reducing that loading to just 1.2% achieves excellent nitrogen gas production at high temperatures. Lastly, we consider the physical limits of these monolithic systems. Mass transfer is governed by geometry. Metallic monoliths have thinner walls than ceramic ones, allowing for a 91% open area and faster heating. However, these systems are prone to severe deactivation. High temperatures cause sintering, where active metals clump together and lose surface area. This is why chemical stabilizers are critical. Without them, the wash coat would collapse, making it impossible to meet the strict 120,000-mile durability requirements of modern law. Ultimately, the research illustrates that the modern catalytic converter is a masterpiece of integrated engineering. We investigated how the monolithic structure must balance chemical kinetics with physical heat transfer to be effective. As standards demand conversions as high as 99%, the industry must master the selectivity of these catalysts, ensuring that engine efficiency does not come at the cost of air quality.
Moving on to the next part of our report, this section will discuss the reactor hydrodynamics, catalyst properties, scale-up challenges, and design consideration for monolithic catalysts used in automotive exhaust systems. For discussion, hydrodynamics and catalyst properties, in monolithic automotive catalyst performance is governed by both reactor hydrodynamics and catalyst material properties. As shown in this wall flow honeycomb monolith design, the catalyst consists of many small parallel channels that guide the exhaust gas through the structure. This design provides a large surface area for reactor while maintaining relatively low pressure drop. Uniform flow distribution through this channel is critical. If the exhaust flow is uneven, some channels receive more gas than others, which reduce the overall catalytic conversion efficiency. There is also a trade-off between gas velocity and residence time. Higher velocity improves external mass transfer to the catalyst surface, but it decreases the time the gases stay in contact with the active sites. The reactions occurring in the monolith are also highly exothermic, which can create temperature gradients that affect catalyst stability. At the material level, the wash coat layer on the channel walls contains porous materials and dispersed noble metals. Wash coat porosity controls internal diffusion resistance, while noble metal dispersion determines the intrinsic reaction rate. Therefore, the overall catalytic performance depends on the interaction between the honeycomb, reaction design, flow behavior, and particle scale transport phenomena. When scaling from laboratory testing to the automotive system, additional challenges arise. For scale-up challenges, first is cold start performance. Catalysts are less active at low temperatures, leading to delay light-off and higher emission. Second, strong exothermic reaction can cause thermal shock and noble metal sintering, reducing catalyst lifetime. Flow maldistribution becomes more significant at full exhaust scale. Long-term exposure to sulfur, high temperature, and contaminants causes catalyst aging and poisoning. Finally, mechanical vibration from vehicle operation can damage the monolithic structure. This factor make industrial performance more complex than laboratory conditions. Now, for conclusion, to address these challenges, optimization strategies focus on both structural and material improvements. Structured honeycomb designs reduce pressure drop while maintaining high surface area. Advanced wash coat materials such as ceria zirconia improve oxygen storage capacity and thermal stability. Modern vehicles use stage catalyst system, a closed coupled catalyst for fast light off and an underflow catalyst for complete conversion. Computational modeling is also used to optimize flow and temperature distribution. In conclusion, monolithic catalyst performance depends on hydrodynamics, mass transfers, and material stability. For effective engineering design, we recommend implementing staged catalyst system, optimizing wash codes, structure to balance diffusion, and pressure drop, and improving novel metal thermal stability for long-term durability. That concludes our discussion on monolithic in automotive exhaust system. Thank you very much for your attention.